So in this example, we're going to be comparing pay periods for compound interest. So again, compound interest, that's the future value for compound interest. That's FV. That's equal to our principal, our initial amount. 1 plus the rate. Now the rate has to be divided by the number of compounds, because the rate has to be divided up throughout the year equally. So then this percentage is going to be applied to this principal so many times throughout the year. How many times is that? Well, we raise it to the n power. Then, of course, the life of this loan could go on for several years. So then we just multiply this to the time. Now we have these different compoundings here, as you can see. Compounds are determined according to a year. So for A, quarterly, how often does that occur in a year? Well, that means the number of compounds is 4. Monthly, that's probably the most popular. There are, how often does monthly occur in a year? That's 12 months out of the year. Weekly, there's 52 weeks in a year. Daily, well, there are 365 days in a year. Leap years don't count. Every hour. Well, since there are 365 days in a year, 24 hours in a day, 365 times 24, that is 8,760 pay periods. That's how often the compounding occurs in 1 year. Every minute? Well, if there are 8,760 hours in a year and there are 60 minutes in an hour, we just multiply this by 60. The number of pay periods, that's 525,600. That's how many times the compounding occurs in 1 year, over 500,000 times. So now we have determined the future value, and we have $5,000, that's our principal, earning 6% annual interest. And this is for 1 year, and then we have these different compounds. So I like to go ahead and list the variables. So for the principal P, that's $5,000. That's a good habit to get into, to just go ahead and list everything that you know is available. Then apply the correct formula or equation, and then do the arithmetic from there. The interest rate, that's 6%. That's 0.06 as a decimal. The time is only 1 year. That's convenient. And then the number of compounds, well, we're going to do it for according to what each one of these is laid out here. So then our future value for A, quarterly, that's equal to our principal, $5,000. 1 plus the rate of 0.06 divided by the number of compounds for quarterly, that's 4. How often does this rate affect this principal? 4 times in the year, raise it to the 4th power. How many years? We're only talking about 1 year. So the first thing we could do is we'll determine the 0.06 divided by 4. So on our calculators, 0.06, divide that by 4, and that's 0.015. So this is 5,000. 1 plus 0.015 is 1.015. 4 times 1, I'm just going to raise it to the 4th power. So now we have 5,000. And I'm going to take 1.015. Here's my caret key. Raise that to the 4th power. Since we're just talking about 1 year, I'm not going to multiply to 1, but just for the sake of exercise, we'll go ahead and do it. And hit enter. 1.06136355. So finally, I'll take the 5,000, multiply to this right here, 5,000 times 1.06136355. Hit enter. And it comes out to be $5,306. And don't forget, we're going to round it to the nearest penny and 82 cents. Now, keep in mind that as the number of pay periods increases, the more the compounding or the piling on is going to occur. And that's a good thing because that interest rate is accruing, or the rate of return is happening more often. However, as the number of compounds increases, 52, 365, that's every day. But as we get into these thousands and these hundreds of thousands, then this value right here, 8 decimals, isn't going to be accurate enough. We need more. Because as the number of compounds increases, the accuracy has to be a lot more precise. So rather than go ahead and do it this way where we have to figure out each individual term in here, we're just going to go ahead and type this in just as we see it right here. So I'm going to clear this out. And I'm going to put down 5,000. Put in the parenthesis 1 plus 0.06 divided by 4, and then close off the parenthesis. So can you see how this looks just like this here? Here's my caret key. I'm then going to raise it, and I'll go ahead and I'll do 4 times 1 power. Hit enter. And we have our $5,306 and, of course, 82 cents, which is what we came up with over here. So doing it this way on our calculators is very effective when our compounds get very large. So we're going to do the rest of them just like this using our calculator. So for B, we have a future value. Let's equal to $5,000. 1 plus 0.06, except now we have 12 compounds. Divide that by 12. How often does this compound affect our principal here throughout the year? 12 times. What is the life of this loan? 1 year. So we'll do $5,000. 1 plus 0.06 divided by 12. Close off the parenthesis. Again, can you see how this looks like this? Use our caret key and raise it to the, I'm just going to raise it to the 12th power. We know that 12 times 1 is 12, and leave it at that. Hit enter. And this comes out to be $5,308 and 39 cents, again, rounding to the nearest penny. So it seems to make sense that as the number of compounds increases, the rate of return increases. We went from $5,306.82 with 4 compounds up to $5,308.39 with 12 compounds. More compounds, bigger return. Let's try C. $5,000 times 1 plus 0.06. Except this is 52 compounds. This compound is going to affect our principal 52 times out of the year for the life of the loan. This just happens to be 1 year. So 5,000 times 1 plus 0.06. Divide that by 52. Raise it to the 52nd power and hit enter. Again, we're going to round to the nearest penny, so that comes out to be $5,309. Look at that. So we could see it's still going up. We have $5,306.82, $5,308.39, $5,309. So the difference in the increase from this one right here to this one over here, that's what, $1.57? But the increase from here to this one right here is 61 cents. So it seems as though we're getting a higher rate of return, but as the compounds increase, the rate of return isn't as much, right? So let's try 365 days. That'll be 1 plus 0.06. Of course, we divide by 365 pay periods. 365 times 1 power. We'll do 5,000. 1 plus 0.06 divided by 365. See it there? Then we'll raise it to the 365th power. Hit enter. So now we have $5,309.16. So the difference between the rate of return is getting smaller. Here to here, $1.57. Here to here, 61 cents. Here to here, only a difference of 16 cents. Let's keep going. Let's try every hour. So it's going to be 1 plus 0.06. But we're going to divide that by 8,760 pay periods. Raise that to the 8,760 power times the length of the loan. Back to our calculator. 5,000. 1 plus 0.06 divided by 8,760. We'll close off that parenthesis. Look at that. Then I'm going to raise it to the 8,760th power. So now we have $5,309.18. Look at that. Only a difference of 2 cents. Let's try the final one here. F, every minute. So the future value, $5,000 times 1 plus 0.06, except we divide that by 525,600 pay periods. How often is this rate going to affect our $5,000 throughout the year? 525,600 times. Holy smokes. Multiply that to the number of years. It just happens to be 1. But here we go in our calculator. 5,000. 1 plus 0.06. And you just have to be careful as you type it in. 525,000 600, and close it off. Do you see it right there? Now I'm going to raise this to the 525,600 power. Hit enter. $5,309, and it's still 18 cents. So there was no change. So what does this mean? Well, this means that as the number of pay periods increases, as the number of compounding increases, as it goes off into infinity, the rate of return tends to level off. So whether we have 8,760 or 525,600, as the pay periods increase, the amount of return tends to level off. There's a name for that leveling off. There's a value, I should say, for that leveling off, and that value is called E.